This video presents the supporting materials for our submission to the 2016 International Conference on Humanoid Robotics. In this example, we present a simple obstacle avoidance scenario. The objective of this test is to demonstrate the basic ideas behind task optimization. The robot must move its right hand in a vertical line from the green sphere to the red sphere. At 1 second, an obstacle is inserted into the path and causes the robot to fail to achieve its objective. Through trial and error, the robot is able to learn the underlying cost function which models the task quality degradation generated by this obstacle. Above, you can see how this model evolves over the trials. After each trial, the Bayesian optimization algorithm used in the study provides the next best task parameters to test. This is shown by the blue dot. These parameters are the z-coordinate and time step of the blue waypoint shown in the simulation. After 7 trials, the robot discovers, with high confidence, the task parameters that allow it to avoid the obstacle and complete its task. All task optimization computations occur in parallel with the simulated trials and can be computed in less than the time it takes for the robot to reset itself for the next trial. This simulation presents a more complex scenario where the dynamics of maintaining equilibrium and moving a 1 kilogram cube are incompatible. The robot is standing in contact with the ground and maintaining equilibrium by keeping the projection of its center of mass centered inside the polygon of support defined by the feet contacts. The robot must move the cube from the green sphere to the red sphere, but because the cube is very heavy compared to its actuator limits, it cannot displace the cube as desired without disturbing the COM task. Because of this, the cube does not reach the target, the red sphere, with sufficient accuracy. Here we dictate that the cube's origin must be within 3 centimeters of the red sphere's origin. Using the same task optimization, the robot learns the underlying model of the task quality cost function and uses it to optimize the task parameters, which in this case are the middle waypoint XYZ coordinates and time step. The middle waypoint is shown in blue as before. After 11 trials, the robot discovers the optimal task parameters that allow it to generate adequate acceleration in the beginning of the movement to overcome the dynamic incompatibilities and get the cube to within 3 centimeters of the target. Again, the same task optimization algorithm used in the toy obstacle avoidance scenario is able to resolve this far more complex example in a comparable number of trials. To show that the robot truly attains the target location for the cube, we plot the distance to the goal for both the original and optimized tasks side by side. For more information and details, please read our submission for the 2016 International Conference on Humanoid Robotics.